Okay, so since I didn't get to bring the practice problems home from work today, thanks to the storm, I just kind of blanked on thinking about taking those. So we're just going to go over a quick review session. So we have a merry-go-round, and on the merry-go-round I'm going to put Mary. So Mary can go round. Our merry-go-round is rotating in the counterclockwise direction. And Mary is our pink dot. Okay, and she's riding on it, and her direction of motion would follow that of the merry-go-round. She's at a distance to start off with of R1 from the center, from the axis of rotation. And at that point, Mary has mass M. And we could say that Mary's angular momentum, L, at point 1, is going to be equal to her moment of inertia at that given point, which is going to depend on her radius from our distance from the center, times her angular velocity. Now, if this is a merry-go-round like the old merry-go-rounds on the school playgrounds, you give it a push, and assuming it's nearly frictionless and it's been maintained really well, it's going to spin with that given amount of energy that it had input into it. So it's spinning, and now Mary decides that she's a little bored where she's hanging out, so she's going to move further out towards the edge. Okay, so Mary walks out towards the edge, and now she's at a distance R2 from the axis of rotation. Obviously her mass didn't change. Mary's angular momentum is now I2 times angular velocity 2. So what changed when she moved out? Her distance from the center changed, and that adjusted her moment of inertia. Okay, because her moment of inertia is dependent on her distance from the center. So for R2 at point 2, her moment of inertia is larger because her radius is larger. So if I2 is greater than I1, what happens to her angular speed? Well, her angular velocity has to adjust if the angular momentum is conserved. So conservation of angular momentum. Okay, and angular momentum is conserved as long as no outside torques were applied. Okay. Well, Mary didn't do anything. She just walked out from the center, right? She didn't apply any kind of a torque, and she's internal to the system. So no matter what Mary does, she's not affecting that angular momentum because she's internal to the system. Okay, so if the angular momentum of the disk plus Mary is conserved, and we look at this as being the angular momentum of the disk plus Mary, then we could write a conservation equation. L1 equals L2 for the disk plus Mary. Okay, and we could substitute in there, and we can set up a ratio to solve for whichever angular velocity we want, or whichever angular or whichever moment of inertia. Okay. Let's say Mary starts to get bored, and her friend Joe comes along, and Joe decides that he is going to take a flying leap tangent to the direction, to the edge of the merry-go-round, and he's going to do that flying leap opposite to the direction of the rotation of the merry-go-round. And then he's going to hang on to the edge of the merry-go-round. Once he hits it, he holds on. Okay? Well, what happens to the momentum of the system? Well, it kind of depends on our definition of the system, right? If we're looking at the system as being just Mary plus the merry-go-round, their angular momentum is going to decrease because now Joe has come along and pushed opposite to the direction of the merry-go-round rotation. And so he's slowing it down. So if we look at it from just the perspective of Mary plus the merry-go-round, the angular momentum decreases. If we take the perspective of the system being Mary plus the merry-go-round plus Joe, then angular momentum is conserved because nothing is applying an external torque. Yes, Joe's applying a torque, but now Joe is internal to the system, so that torque doesn't matter. Okay. Next scenario. Mary is riding the merry-go-round. And the merry-go-round is still moving in the counterclockwise direction, we'll say. And Mary decides that she's going to take a walk in an arc in the same direction as the motion of the merry-go-round. What's going to happen to the angular momentum of Mary? What's going to happen to the angular momentum of the merry-go-round? What's going to happen to the angular momentum of Mary plus the merry-go-round? Well, if we look at the whole system as being Mary plus the merry-go-round, her moving this direction really doesn't have any impact, right? Because if she's moving this direction and she's internal to the system, she can't impact the angular momentum as a whole. If we look at just Mary, if the platform is rotating this way and Mary starts walking this way, Mary has just increased her angular velocity. Okay? So if Mary's angular velocity increased and her moment of inertia stayed the same, right? Because she didn't lose mass and she didn't change her radius. All she did was increase how fast she's moving this direction. If that's the case, then Mary's angular momentum increased. Angular momentum of Mary increased. Well, if she's increasing her angular momentum, and we said the angular momentum of the system as a whole stayed the same, what happens to the angular momentum of the merry-go-round? Just kind of one to think about. Okay, moving right along to inclined planes. If I have a sphere and a cube, and the cube is sliding down a nearly frictionless, essentially frictionless inclined plane. And the sphere is rolling without slipping down an inclined plane. Which one is going to reach the bottom of the inclined plane first? Well, let's look at it through conservation of energy. If this one starts off, assuming that they both start from the same height, PE initial equals, and assuming that they both have the same mass, mgh, and it all gets turned into kinetic energy at the end. So conservation of energy says PE initial equals KE final. Well, if it gets turned into KE at the end, and it's rolling without slipping, the KE at the end is going to be 1/2 mv squared, because it does travel in a linear, it travels linearly down the ramp, so it has translational motion, but it also is rolling, so it has rotational motion, so it also has 1/2 moment of inertia times rotational velocity squared. Okay, and that's for the sphere. And how fast it gets to the bottom is determined by its velocity, right? Because they're traveling the same distance. So we're going to call this the velocity of the sphere and angular velocity of the sphere. Okay, for our block, it has PE initial equal to mgh, because we said the sphere and the block had the same same mass, and they're being let go from the same height. At the bottom, the block has KE final equal to 1/2 m velocity of the block squared. And it's not rotating, so it doesn't have anything that goes to rotational velocity, so no rotational kinetic. So for the block, PE initial equals KE final. And we can say for the block that was 1/2 mv B block equal to mgh. And for our sphere, it was mgh equal to 1/2 mv sphere squared plus 1/2 moment of inertia, rotational velocity of the sphere squared. Okay, so if we were to look at those two, the sphere has to have a lower velocity in translational motion because it's lost some of its energy to this component here. If it's lost some to rotational, it can't have as much for translational, so it's going to have a lower velocity. It's going to take a longer time to reach the bottom of the ramp than would a block on a frictionless inclined plane. If you start looking at this as having friction, then you would have to actually have some percentage that it's being lost to friction in order to compare and see how much is being lost to which. They'd have to give you a radius for this and some more information. But if it's just a straight up choice, then you need to pay attention to which one is losing more to rotational energy. Okay? If we had a third situation where it had a larger sphere, okay, on an inclined plane, and let's say that this had the same mass, and we wanted to know which one was faster getting to the bottom, this one or this one. So larger sphere or smaller sphere. Well, if we look at it, if they're both mgh to start with, and they're both going to have some translational velocity and some translational kinetic energy, so how much translational velocity they have is dependent upon how much they lose to the rotational. How much they lose to the rotational kinetic energy. And how much they lose to this component is going to depend on their I value. Okay, so if their I is based off of M and R, if M stays the same, then it's dependent upon their radius. Okay? So hopefully that helps in differentiating between those problems. All right, guys, get some rest tonight. If you're super stressed out and want to go through more problems, go through the AP Practice 5 Steps to a 5 book that came with your textbook, and I'll see you tomorrow.